What's up, guys? Last video on calculating Kc. I'll put the link to the first video here if you haven't seen any of these. Before we start though, please like, subscribe and share. Let's get into it. So, one point I haven't made yet is generally when we're looking at Kc at A level, we only see what we call homogeneous reactions. Homo meaning same, and in this case what we're talking about is in the same state. So we're talking about gaseous state molecules when we're talking about equilibrium constant, particularly at A level. Now, let's get into a question. So 2 moles H2N2 heated at temperature T, so this needs to be constant, in a vessel with a volume 2 decimeters cubed. So we've got CNV. I know at some point I'm going to need to divide by that 2 in order to work out my concentration. Equilibrium, 2 moles of H2, 2 moles of N2, 1.2 moles of NH3. So, calculate Kc at temperature T. So, this is our reaction. First thing we need to do is we need to fill in our table. We need to do our ice. So, our initial moles are here. 2 moles of H2, 2 moles of N2. So, I can put that in 2. 2, and we're going to start off with 0 of NH3, as will always be the case. Equilibrium mixture contains 1.2 moles. So my equilibrium mixture contains 1.2. Now I need to work everything else out. So this plus 1.2, and now I use my molar ratios to work everything out. So if I've gained 1.2 here, I've lost stuff over on the other side. Here, 2 to 1 ratio, I need to divide that change by 2, so minus 0.6, sorry. And there I get to 1.4. For H2, I need to minus 3 lots of the minus 0.6, so minus 1.8. And there I get to 0.2. Now remember, I need to work out my concentration before I finish. So I need to divide everything by 2 here. So I get to 0.1, 0.7 and 0.6. Now, I need to use this information and put it into my expression for Kc, which we've not done yet. Remember, that's always going to be our concentration of products. And it'll be squared because of this 2 here, over our H2 to the power of 3 because of our 3 here, multiplied by our N2. Now I plug my values in. So I've got 0.6 squared over 0.1 cubed times 0.7. Plug all of that in and I get to 514.29 if I round at the end. Now, one thing I'd say here, the section I would use on my calculator is this one, where we've got this symbol. And I'd literally type exactly what I've typed here. The 0.6 squared all over the 0.1 cubed times 0.7. Yeah, where we write things out like this, I'd make sure my calculator looks exactly the same. Last thing we need to do here is we need to calculate our units. So there. Remember, units for concentration are moles per decimeter cubed. I've got 2 of those on the top. I've got 3, 4 of those on the bottom. And I can cancel, right? So I cancel all of these to make 0. I'm left with 2, which is equivalent to 1 over mole to the 2 dm minus 6. And to bring that to the top, I need to invert all my indices. So our units are mole to the minus 2 dm plus 6. Circular answer. Happy days. Next. Describe and explain the effect of doubling T on Kc. So here what we need to think about is what way is our equilibrium going to shift if we double Kc. So, if we double temperature, sorry. So our forwards reaction, we're told, is minus 92. So our forwards reaction is exothermic, while our backward reaction will be equal and opposite, so endothermic. If we increase the temperature, our reaction shifts to the left-hand side. It shifts to the endothermic side. Now, if we look here, if our reaction shifts to our reactants, that will make this number bigger, which means we're dividing by bigger numbers, which will mean our final value is smaller. So, all in all, we can say, for B, an increase in temperature shifts reaction to the left, which is our endothermic side. Therefore, Kc will decrease as dividing by bigger number. And for part C, describe and explain the effect of doubling pressure on Kc. No effects. If you remember, I spoke on the first video, only temperature affects Kc. And that's just something you've got to remember. So this is the question I want you to give a go. I'll answer that at the end of the next video. For now, let's look at what we did last time. So here, again, working out our reaction moles by doing this. So start off with 0 plus 3. Use my molar ratios 2 to 1, so I divide that by 2, minus 1.5. So here I get to 8.5. And if I was working out the concentration, I'd be dividing by my volume here. Next, A, B, C, D. So here, plus 2. So we start with 0, 0 plus 2, minus 2, and minus 2. It says here, why doesn't volume matter here? Now, I'll quickly explain that. Kc equals, if I do my expression for this, again, we've got C, D, A, B. Now, if I put this here, so I've got C, we had 2. And remember, we need concentration here. So for concentration, we're going to divide by the volume. Multiplied by, again, 2 divided by volume, all over A, 0 divided by volume, times by 0 divided by volume. Really, we don't want to be working with 0, that 1 divided by volume, sorry. We don't really want to be working with 0, but let's ignore that for now. Essentially, because we've got the same number of V's on the top and the bottom, they cancel out. All right. So if we ever get to a point where the moles on our product side and the moles on our reactant side are equal, V will cancel out when we put it into our equation for Kc. So here, volume cancels. Hope that's helpful. Give the other question a go. See you next time, and until then, happy revising.